Let's talk about the worst case time complexity to construct a minimum spanning tree. Here I've reproduced the Prim's algorithm and Kruskal's algorithm pseudocode, two different algorithms for finding a minimum spanning tree in a graph. Let's start with Prim's. Basically, I start my algorithm at any arbitrary node, and then for each edge that I need to add, I find the smallest weight edge starting from one of the nodes in my growing minimum spanning tree and going into a node that's not in my minimum spanning tree, and I add that edge to my growing minimum spanning tree. Well, how would I actually implement this? If you think about it, theoretically, I could have all of my edges coming out of one node. For example, what if I happen to start at this node and every single edge in my graph stems from this node? In the worst case, I would have to have some quick way of finding the smallest element in a list of possibly big O of number of edges, total elements. And whatever this search is doing, whatever this find the smallest weight edge, I should be able to do it throughout my entire graph traversal. So I should be able to add edges to my collection of edges to look through, and I should be able to remove edges from it. So hopefully this makes you think, well, I should be keeping a priority queue implemented as a heap. Basically, I can have a priority queue of all of the valid edges I can search, and at the beginning, I'll add all of the outgoing edges from my starting node, and throughout this traversal, finding the smallest weight edge would simply be removing the next element from the priority queue, which is big O of log of number of elements, so big O of log E in the worst case, where E is the number of edges. And then I would add the edge that I just removed from my growing MST, and then I would also have to insert all of the new edges that stem from the node that I added. So for example, let's say I have this graph, and let's say that I start at this node. I would have to add these 6 edges to my priority queue. And let's say the next iteration, so when I enter my loop, let's say this is the edge that is the smallest weight edge. When I pop it out, I would have to add all of the outgoing edges from the node that I've added back into that priority queue. So in the worst case, if I have E edges, I would have to add and remove, or at least add. I would have to add every single one of my E edges to a priority queue, which as I'm implementing as a heap, this would be big O of E log E. So overall, the time complexity of Prim's algorithm is big O of E times log E. The slow step is potentially adding big O of E edges to a priority queue that's implemented as a heap. And then throughout my search, I have to remove some nodes, some edges. What about Kruskal's algorithm? Well, basically, I want to iterate over the edges in increasing order. So for me to do this, it makes sense for me to first sort the edges in increasing order. Well, we know that if I want to sort a list of n elements, this is big O of n log n. If I want to sort E edges, this would be big O of E log E. So this is big O of E times log E to sort my edges, and then iterating over them, well, this is just constant time per iteration, and adding the edge to my growing subgraph. We haven't necessarily learned about the uptree data structure yet, but it turns out that I can actually add the edges to my subgraph and check if they'll cause a cycle or not by using an uptree in constant time. So the contents of this are actually constant time, assuming that I've already sorted my edges. And I'm doing big O of E constant iterations, so the contents of this are actually less than the time complexity of even just sorting my edges. Right, so this would be big O of E, each of these iterations. I could theoretically implement this such that these two operations happen in constant time. So overall, this portion of the algorithm is big O of E, but just from sorting, this becomes big O of E log E. So notice that regardless of which algorithm we choose, the overall worst case time complexity is big O of E log E.